Yeah, hi everyone. Welcome to our first lecture here under our new brand GPU mode. Today I am glad to have Kapil Sharma here, who will give a talk about the internals of the Triton compiler. So as a background, Kapil got father in August, and during this time he wrote a 3-part blog post about the Triton compiler internals, which I also asked him then, if he could do this like also in the video presentation form, because I think it's super relevant to a lot of people, are super interesting. For example, I myself was always curious to learn about what's behind the Triton surface, which I used most of the time. I only looked very briefly into the source code and so on. So I'm very glad that he's here today to talk a little bit about the internals and to so that we are now basically can learn something about the magic which is happening invisible in the back end of the Triton compiler. Yeah, just as one note, normally this takes like 1 hour. For talks, if you have questions, please use the reading group chat, which we will then try to forward to Kapil during the talk. And as a general note, Mark was very active into getting a new speaker, so we will have a lineup. We have a super great lineup until basically Christmas this year. So check out the events tab, register for the upcoming events. Yeah, Kapil, I may now hand over to you. Please get started. Thank you very much for coming.
Sounds good. Hey everyone, I'm Kapil. And I'm an engineer at Meta. I primarily focus on Vexus ranking focus infra at Meta, but love Triton. So this was essentially, the blog posts came out of just my interest in ML compilers. So I just wanted to dig into Triton, and that's where all of that content came from. So about me, I sort of already mentioned that I work in Meta. So this is my public info if folks want to reach out. Now, we've had a series of talks on Triton before. We've had the original Triton kernel talk, Triton 101, where we learned how to write Triton. There was a fusing kernel talk using Torch compile, which I did a few months ago. And then there was a recent Liger kernel talk as well. Why Triton? I guess I don't need to convince folks in this group. Triton is loved by researchers and engineers, and it's essentially has reduced the research to production time for researchers. Like you can get a research idea into production fairly quickly just using Python style DSL, which gives you a near optimal performance, and in some cases better than sort of the libraries from Nvidia. And now, what we see on the surface is essentially like a Python style code, right? And what under the hood, Triton is fairly complex compiler and code generation machinery. It does a lot of cool stuff for you. Kudos to the Triton team on that. And there has been a lot of work happening in the Triton space for the last 2 years, so which we'll cover a little bit as well. But yeah, the reason why I'm personally interested in Triton is essentially my motivation is I can write PyTorch and I can use Torch compile to generate a Triton kernel, and then I can target any specific target hardware from there. I'm sure folks who were there at the Triton conference, I wasn't, unfortunately, but there were some really cool talks on recent developments working on Intel GPUs. There were also Triton CPU work, and there were some talks on the custom chips as well. So a lot of cool stuff happening in this space. And if you want to look at the blog post, I also linked them in the slides here. Now, in terms of agenda, we'll briefly cover the CUDA and the Triton compilation process, like how it works. We'll go over a simple Triton kernel example, and also go through the JIT compilation process, like how that works. After that, we'll dig a little bit into how Triton uses MLIR and do a little bit of an IR walkthrough, essentially what Triton generates under the hood. And from there, we'll hopefully, if we have time, we can probably write like an example compiler pass in Triton compiler, something very simple like a hello world. Now, I'm sure a lot of folks are already aware of how CUDA compilation works, and I don't claim to be an expert in it, but I essentially just briefly cover it at a high level. Essentially, whenever you're compiling CUDA targeted code, you will, so NVCC toolchain will take your host code, compile it using a standard C++ compiler like GCC Clang, and also the device code gets compiled down to your PTX or a fat binary Cuban, and then everything gets linked together to a standard C++ compiler to give you an executable. This was a slide that I found in one of like Nvidia's conference talks, which covers it in much better way than the text that I had in the previous slide. Essentially, you take the front end CUDA C++ code, goes to the CI/CD optimizer, generates PTX assembly. Then you have the host code, goes to the host compiler. Everything gets linked together to get a CUDA executable. Folks who like worked with Compiler Explorer or Godbolt website, you can actually see the actual PTX and SAS for a specific kernel there as well. It gives you a fairly old version of the SAS, but I mean, that sort of doesn't matter. It's just like, it's a useful tool, in my opinion. So this one's just a standard, you add vectors kernel, you take A and B, output to C, and you can see like exactly the PTX here. And yeah, this is where sort of most of the work is happening for the kernel. I'm sort of just rushing through these slides because these are sort of just to build a little bit of a background. Now let's this graphic is from the OpenAI's article on Triton. So essentially, like so if you go a layer up, like how does Triton compilation work? It goes through several layers of IR lowering, starting from a common IR, which is Triton IR. What I mean by IR is essentially like an intermediate representation of your Triton DSL program, which is sort of human readable. And it goes through several compiler passes to be lowered to Triton GPU IR and eventually to LLVM, and then you get PTX assembly. Now PTX then gets converted to essentially it's a Cuban, a binary that gets loaded. Either you can load it as just a kernel or using like CUDA drivers, or it gets JIT compiled as part of the Triton JIT compilation process. So we'll cover that in a little bit. And the Cuban is just essentially like a standard ELF formatted file. It's a pretty standard binary format where it essentially has a header with a bunch of artifact or like metadata on like what the binary is. So yeah, it's a fairly standard like C++ binary format. This is a slide from one of the, I think this was like Triton compiler talk from PyTorch conference last year from 2023. This captures everything pretty well, but I think this has expanded based on like this year's, based on learning all about all of the developments on Triton front. So your Triton DSL, see like it gets compiled down to this common IR. Then for each individual hardware type, you lower it, lower it down to the respective native binary. So this is for the originally for Nvidia, now AMD, Intel, and like for custom accelerators as well. I think there's some of the custom accelerators use vector dialect too. So I think this is sort of old. So there has been a lot of new developments here. Yeah, I want to pause there for a second if there were any questions before I jump into code. If not, then maybe we can keep going. Okay. Cool. Now let's do a little bit. Let's look at a little bit of code. So now this is a standard.
So actually, Kapil, I got a question in chat. So how is the code distinguished between various TTGIR? So I guess maybe go back to the IR slide and go through that.
Okay. How does it get distinguished between different specific GPU IRs? So there are so yeah, it's jumping ahead a little bit, but there are like specific drivers and launchers for each of these. So like the drivers specify like how your IR is lowered for like AMD versus for Nvidia. But we'll cover that a little bit in a little bit. So essentially, you have to target, you have to write compiler passes for individual hardware type. Which is done through like this MLIR ecosystem, or MLIR dialects, essentially.
This might be a silly question, but like, was there a reason why like there's like basically 3 boxes for Triton GPU IR that are splitting into various hardwares? Like, why is that like not a single box and then it spawns into like various other vendors? Is this sort of just a stylistic thing, or are the Triton GPU IRs for various vendors actually different?
That's a really good question. So, based on my research, I think there was the whole backend was rewritten in sort of late 2022 to actually make it modular, so that you can actually target different hardware. So I think originally it was just written for NVIDIA. So now I think there's still work happening. When I was like looking at the code, there are NVIDIA specific stuff that you will see in the Triton GPU IR, but then there's also Triton NV GPU IR, which actually the NVIDIA driver will actually call into. But I think there's this, it's fairly active, this work. So I think there's a lot of work happening in sort of making this generic enough that hopefully there are parts of the Triton GPU IR that are common, and then you essentially have a hardware specific IR or MLIR passes can be part of a separate dialect. So it's fairly active from what I've seen. Like even in the last 2 or 3 months, there's been a lot of code changes there.
Okay, thank you.
Okay, so yeah, I mean this is just a standard example. The first tutorial that we see when we learn about Triton, the Triton or the vector add kernel. Now I mentioned so you can compile the actual Triton DSL down to your PTX assembly or Cuban. You can do it in 2 different ways. One is you can actually just use a Triton tool, which will compile it fully and actually dump a bunch of artifacts on your hard drive, or you can JIT compile it. Most of the work that's done by Triton compiler is the same, but there are slight differences. So like first, let's look at if we just compile it fully, like what do we get? So let me get my terminal. So what I did was I just took the standard vector add kernel. I just put it in the lectures directory. So I think I'll probably merge that in a couple of.
Do you mind zooming in a bit? If that's okay.
Yeah, better.
Okay, much better. Yeah, thank you.
Okay. Okay, cool. So yeah, this is just your standard Triton vector add kernel, and there's just a main where we just do the standard, like take a couple of rand tensors and just run through it. I also put in like a debugger call, so we can just check like what gets generated by during the actual when we call the JIT compile kernel. So so essentially like I already have the Triton repo checked out. So I'm essentially taking the compiler tool, running the kernel through a compilation process, and it should just dump a bunch of artifacts. But so what I'm going to do is like I already know where the stuff goes. I should have probably mentioned that before. So like so Triton has this like Triton cache directory, which is by default just like your home.triton cache, but you can like override it if you want. So I was just clearing it to just make sure there was nothing there, right? So it's just be empty. I'm just gonna run the compile command now. So it should dump a bunch of artifacts there. So here you are. So like, let's check here. So if you see here, it drops all of your progressive IR in this directory, and it also drops your actual binary over here, and also has this like shared library, which is CUDA utils. Now, if you wanna like look at what some of these are, let's just like print it out on the terminal. It should look something similar to what we saw in that Triton or like the OpenAI Triton page. So like essentially this is the first common IR, the TTIR. So you'll we'll probably so I guess we will cover the actual like going through an IR walkthrough later, but some of these things should be sort of easy to follow. Like you have the program ID, then you have essentially here's where you're generating a bunch of indices, etc., etc. There's going to be some add pointers, stores, loads, all of that.
So Kapil, like there's a bunch of questions in chat. And sorry, like the general theme in our service, people love to interrupt our speakers. So please bear with us.
That's fine. Yeah.
So pseudo terminal X is asking a very interesting question. It's just saying like, as Triton can leverage LLVM for compiling into HIP kernels, does this mean that like we can leverage something like tinygrad to compile metal kernels? And I think the question is trying to get at like which layer of IR can we plug into, and how should people like basically think about like what kinds of things they can express using MLIR?
Yeah. So again, I'm not an MLR expert or like sort of, but my understanding is like I think the Triton IR is supposed to be the common IR layer. I think you can hook into any of the layers as long as you can swing it, right? Like as long as you can get your custom or like whatever custom DSL that you have. I don't know enough about metal. Unfortunately, it is something on my like to-do list to like play around with it. But essentially, it doesn't really matter as long as you can get. So as you go higher up the lowering chain, it is easier to understand. So like, or it's probably easier to generate that level of IR from whatever program you're writing. So, but my understanding, I think like Triton IR is expected to be the sort of the common IR layer. So if you look at the actual the most recent project, which was Triton CPU IR, so I think there's a PR to add like an inductor backend to PyTorch, which will allow us to write or actually generate Triton kernels for CPUs. And then you essentially can lower that down to your x86 assembly, right? So that actually, it leverages the common TTIR, and then it diverges from there to like TTCP CIR, essentially. So I mean, but yeah, I again, I don't claim to be an expert, but that's my overall understanding.
So you touched on lots of interesting ideas. Like I think one is, so first off, if folks are interested in metal, we have like Nikita Shulga, who's like one of the maintainers for metal and PyTorch, who's going to come give us a beginner's guide in 2 weeks. So if you're interested, please check that out. I think like Kapil also kept like mentioning the Triton CPU backend, and personally, I feel like this is so compelling to get like decent performance for both x86 and for ARM as well. And part of the name rebrand was like, we're interested, in more hardware architectures. So like, if this is like a space you're interested in following, we have a couple of working groups and some of like the world's experts like now like basically checking in there. So sorry for that plug, but Kapil, please go ahead.
No, that's fine. I mean, honestly, like my whole motivation to play around with Triton compiler was I wanted to write a kernel that I could run on my Raspberry Pi. Essentially, like, can I write a Triton kernel and target my Raspberry Pi to maybe, I don't know, like record my video and essentially take a bunch of pictures of me, something like that, or like essentially identify my face. Can I do that with Triton? I think like once you have a common IR layer where you can just target to specific custom hardware, I think that's going to be amazing. Yeah.
All right, I think you got Chad excited. Yeah, so we'll stop interrupting you. Please keep going.
Yeah. Okay. So another thing. So when you run the actual compiler tool, it will also drop this the two files like this, just the header files, which is not super interesting. Like this is the one. So if we dig into it, I actually just so that it's easier to look at, I put it on a gist. So what it does is actually, let's look at it in raw form. So yeah, we talked about Cuban, right? So essentially, like what it's doing here is taking the actual assembly, it's just inlining it all over here, and then it's just using a bunch of Nvidia driver functions to load this inline. So this is essentially like a CUDA module. You compile, you essentially now target this function, which is essentially the kernel, and then you can call and launch this kernel from here. So this is essentially a kernel that's generated by Triton, and then you call back into just this custom assembly. So so if you do any if you compile using the tool, this is what you typically get. And sorry, there was oh. Now, I already sort of talked about this. So essentially, like it generates five different files. For NVIDIA, it could be different for different hardware types. Really depends on how many layers of lowering you're doing and when you're dumping the as part of the compilation process. I also found this some interesting tools to play around with these. So like since I said like this is just an ELF formatted file, so you can just use your standard read ELF to read this. Just makes it easy to read it in like human readable form. There's also like a couple of NVIDIA tools which you can use to read through these. I mean, this one's standard. It just takes the Cuban. It will just dump the SAS and PTX. This was interesting, so I wanted to show this. So we had let me just quickly look at where. Okay, so this is the directory. So just gonna add kernel Cuban. Let's first, it's just a bunch of gibberish, but actually. So now it becomes like a lot more human readable, right? And you can see it actually gives you instructions by where the actual call is coming from. So it's essentially giving you like, oh, this is a move register call, or things like you will have like integer add, stuff like that. So this, I mean, again, I'm like, I don't think anybody really needs to look into it, but it's just something curious that I found when I was just like researching for it.
Okay, but and one question,
Now,
like the hash code that we see there, like is so it is basically a compilation. Is like always a different one is generated for each combination of constants or whatever you put into the kernel, when it basically then dynamically compiles this like combination. Like you get these couple of files for every like part like combination of parameters which go into the kernel, right?
do you mean these SSA instructions? Essentially,
No, I mean
these
like all
ones
the files which are generated in this cache directory, like basically all the
yes,
compilation.
I'm not sure how the hash works, because the hash. So like if you run the same kernel twice, it actually maintains the same hash. So so there's actually like a bug that I found too. So I think like I'll cover that later. But if you call the same kernel twice, it won't regenerate the hash. But yeah, so based on the combination of argument that you're passing into the compiler, it will regenerate that hash into something different.
Okay, and this is like stored in the JSON file, or what is the JSON file in the directory?
Oh, JSON file, I think it has a bunch of artifacts. So if we, okay, let's go back here. So it was, so there are two separate JSON files, right? Yeah, there's one here. So let's just print this one, add kernel JSON. I think it has so it just tells you, okay, it's targeting backend, CUDA backend. So funny story, I had my 4090, the machine that has a 4090 is having a fan problem. So a lot of the code some of it will say SM89 and some of it will say SM75. So apologize for that. So yeah, unfortunately that machine hasn't been working for the last couple of days. But anyway, the somebody sorry, somebody just ring my bell. I have no idea. Oh yeah, so sorry, so going back, so yeah, it's telling you like specific specifications for the backend that it's targeting essentially.
Yeah, so for example, if you
that-
would like call it now with an FP16 or yeah, tensors, then it would obviously like need to regenerate it, and then probably would
yes,
get something which would say like allowed input precisions or
I
something.
think so. Yeah, so think there's, so yeah, it's saying like, oh, dot tf32 allowed dot in. So yeah, there's a bunch of stuff in here. So yeah, I'm assuming, assuming it will. So if you change the actual like the D type that you're targeting for the kernel, it will probably change. It will change the hash, and essentially it will dump the exact like JSON with the targeted D types and targeted backend, etc. There's also this one, which I think has like more like some other information. Now, oh, I see. This is just pointing to like where the actual IR files are. So I'm assuming that this JSON gets used by the actual like the JIT compiler to like load like for example the binary or something. Cool. So going back, okay, yeah. So I was talking about the tools. So yeah, there's a bunch of tools to like play around with this with the CUDA binary format. So yeah, I just linked them here. Now there's another way to compile the kernel, which is when you just run a kernel, you will actually get all of this compiled for you as well. Now I'm just gonna clean up my Triton cache again, just to make sure that I'm honest, that everything is regenerated. So in this case, I'm just gonna run the vector add kernel. So there you go. It should probably drop into the debugger this time. Okay, yeah. So we have this compiled kernel. So within this Triton compiled kernel, you have all of the artifacts that are actually dumped in the Triton cache. So so let's look at TTIR. It should look identical to what we saw earlier. This is probably better. Yeah. So yeah, same process, but in this case it just keeps everything sort of in memory, and just in time runs the code. Ignore this. I was just using the get sass function to actually there's a get sass function in the Triton tools where you can just pass the Cuban to get the actual sass for. But yeah. Now, so yeah, so we covered essentially a bunch of things, right? So like your Python DSL gets compiled through multiple layers of IR down to PTX, down to Cuban, and actually we should check again that so we just this time around it actually generated 3 directories instead of 2. If you remember previously there was this CUDA utils, so now you have this Triton launcher shared library as well. So but we don't get that the add kernel.c.header file. So what my understanding is, like it essentially this all is then just compiled down to a shared library when you're using just-in-time compiled Triton kernel. So, but yeah, it just dumps this on your hard drive as well. Now, already mentioned that there's a Triton cache directory. You can always override it to put your Triton cache somewhere else. Now, each individual, I think we covered this early on, that each respective drivers would actually put like different set of files on your computer. We can probably, I think if we have time, I do have the Triton CPU repo checked out, but it's just like the actually rebuilding everything takes about 3 to 4 minutes. So if we have time, maybe we can try out like the Triton CPU at the end too. But yeah, I have seen like you can actually see for Triton CPU, you get TTCIR, and then you actually get the x86 assembly because I have an Intel machine. Now, so yeah, it exports these to shared libraries. If folks are interested where these come from, I just put in like code pointers within the Triton directory. So like if you're interested, like I think, so this is the Nvidia backend. So like if you go into third party, you'll see a bunch of backends here. So like AMD will have its own thing. There's the Proton backend and whoops. And yeah, essentially just takes a C file and dumps it into a shared library. But yeah, I mean, nothing super crazy, but yeah, it's like this is where everything, all of the magic happens. And there's again this like build process, which is common within the actual Triton Python package. So essentially, all of this is packaged with the actual Triton bit package example. But how do you get this IR? like nobody. So this was funny. So I was just like trying to figure out like how does this IR come from? So one does not simply handwrite this IR. So Triton. So this is what we just previously covered, right? So the whole backend was sort of rewritten to make Triton work with MLIR ecosystem. So essentially, Triton heavily uses the MLIR ecosystem. Now, MLIR, the ML in the MLIR is not machine learning; it's multi-level intermediate representation. So essentially, what it does, it provides you a toolkit to write compilers. What that essentially means is there are a bunch of tools as in the MLIR ecosystem which you can use to write any compiler, and you can extend it using like custom DSLs. Now, Triton itself uses a bunch of these to essentially define Triton specific DSL and Triton GPU, Triton Nvidia GPU, etc. Now, all of these extensions happen through a concept or like through a thing called dialects. So these dialects essentially provide you a mechanism to extend like the already existing MLIR tooling that you have, which essentially means you can just like build on top of or compose your compiler off of already existing tools and build a sort of a more higher level compiler, which a lot of the ML compilers are. One interesting talk I found was from, I think this is from 2020, so which was focused on TensorFlow. I think TensorFlow was the first major ML framework using MLIR. And I think now it's been adopted by a bunch of other projects. So I believe Mojo uses MLIR as well, from what I know. And I believe TVM as well, but I'm not sure. Now, these dialects are essentially, now there is another layers of abstraction that's provided as part of the ecosystem, which is called a table-gen DSL. Table-gen is essentially just a code generation process where you can define your compiler passes as simple like Python looking functions, and then you just like compile it and you get a bunch of like boilerplate code, and then you just have to write your small part of an optimization or a lowering pass in the standard C++. I also provide like a small a resource for like table gen, what that looks like. Now coming back to Triton, if you want to see the IR generated after every single compiler pass that you run, you can actually use this environment variable called MLIR enable dump. Now let's check that out. Again, so now, so this is the bug I found. So if you actually run a kernel twice in a row and you used MLI enable dump, it will only dump the IR the first time, not the second time. So I think that it's like you really have to clean your cache to re-get the IR dump. So yeah, I mean, so I'm just gonna clean out my cache again to make sure we get this dump. Because I think it just ignores this environment variable if the kernel already exists in the cache. So let's so I've already run this command before, so it's here. So now it should actually again stop at the debugger. So let's go up. So it dumped a bunch of stuff on the terminal. It's just huge amount of stuff. But you can see like now it's showing us after every single compiler pass, like what was the state of the IR. So going here, it's doing Triton combine ops pass, Triton to Triton GPU, Triton GPU remove layout conversion. Some of these will look by name will look familiar. GPU reduce data duplication, SCF to control flow. I think the structured control flow. NV GPU to LLVM. This is where it converts your GPU IR down to LLVM IR, and etc. etc. So it just does a whole bunch of stuff in here. Now I think there was a question on the Triton channel around like folks asking around like whether Triton will reorder load and store ops. It definitely does, and you can, if you want to like dig into things like that, like think this is a really good way to like figure out how it's doing that. So you'll probably will have to go through each IR layer, and wherever it's doing any sort of storage pass and changing anything in the ordering of your IR, you can see that pretty clearly in here. I mean, just diffing through each stage potentially. Now, so yeah, I mean, this is a pretty good tool if you want to actually see like why or like how your kernel is being compiled under the hood. Now, just to quickly cover what MLIR is, like this is just, so if you were to have like a programming language that you're compiling, you can have a bunch of compiler passes. So this is, so MLIR, as I said, like MLIR provides a bunch of common passes. So this is just a standard common sub-expression elimination. You just take a common sub-expression, replace it with already calculated value. This is dead code elimination. So anything that that doesn't have any impact on the code, you can just drop it. Or doesn't have any impact on the output, you can just drop it. Which could look something like this, right? So let's say this is your custom language that looks like Python. You want to compile it using MLIR. B plus C is already calculated as A, so you can just replace it here. So this is replaced by CSE. Then you have E into 2 into A. This does nothing for the output, so you can just drop it, right? So this will result in like something like this. Now, how does Triton use MLIR? There are a bunch of common passes that Triton uses first when it generates your TTIR. So some of these will look sort of common for people who have probably worked in compiler space or have at least known people who have or like have poked around with compilers in any way. So this is your constant propagation, your that code elimination, inlining, canonicalizing, common sub-expression elimination, etc. So this is just directly from the Triton repo. These are the common passes that it uses, and it uses it across different IR lowering passes. Now, if you're interested in like what sort of
So Kapil, a question so these passes, were they implemented by the Triton team, or are these like standard passes that like the MLIR team provides?
Oh, so these passes actually exist in MLIR, but so the way Triton uses them is essentially they have bindings. So because all of the compiler stuff is actually written in Python, so they have essentially the SpyBind modules which have all of these exposed into the Python there. So, but these are all sort of standard MLIR passes.
Very cool. Thank you.
So yeah, so I mean, if you curious, like I think you can look at like there's a bunch of these common passes that it provides. So like if you wanna, generate runtime verification pass, I don't know what that does. Strip debug info, print op stats, create inliner pass. So this is the inliner pass that I mentioned earlier.
Okay. So speaking of, there's like 7 questions in chat or so. So I'm just gonna read them all together because they're okay. So Samran, for example, is asking, like, can you model like data flow using MLIR? Apaz is asking, like, can you model synchronization? Dani Khan is asking about like async ops. Rectifies is asking about efficient code generation for multiple architectures. So yeah, I'll just batch all the questions. Feel free to answer them in whatever order makes sense.
Okay, I think like folks think that I'm a compiler expert. I'm not, but sorry. So can you sort of summarize like the type of questions?
So we had efficient code generation for multiple architectures. We had data flow, and we had async ops. Oh, and model synchronization. Sorry.
Okay, got it. Yeah, so I think I don't know about async ops. I don't know if threading is like it provides any threading style passes. Data flow, yes, I think it provides a bunch of like tools to actually like do sort of data coalescing, for example, or like essentially like optimize store loads, which actually Triton uses heavily. And I actually don't know the answer to the third one either. So I mean, I don't know if there are any compiler folks in the crowd. I think they will probably be able to answer it better than me because I actually learned MLI in the last 2 months. So yeah.
It seems like Dana Khan in chat is quite knowledgeable about Triton, so maybe he can so maybe they can field some of these questions. Yeah. In the meantime, Kapil, please keep going. Oh, and also we have Samran, who is a compiler expert. Interesting. Okay, we got the compiler experts in chat then. Very good. Very nice.
That's awesome. I mean, there's Horace too. I think Horace should be probably able to answer. Yeah. That's the person I know. Yeah. So okay, cool. So now, so if you after the common set of passes, like now Triton extends the MLIR like MLIR framework with a bunch of Triton specific passes. So I mentioned table gen before, where so this is what table gen looks like. So whenever you see like transform passes or TD, this is like your table gen file. So now Triton has like a bunch of these specific transformations or optimizations where it's doing. So think this something like this is just fusing matrix multiply add or like essentially like similar to matrix multiply add. This one essentially is combining the actual 2 separate add pointers into a single one. You traverse this one and then you traverse this one. Instead of that, you can just combine these two. And there's a bunch of other ones as well. This one's interesting. So like, I think broadcasting is fairly common operation that's done in most ML frameworks. So like, for example, if you're doing element-wise op on a broadcasted value, you would rather just do the element-wise op first and then do the broadcasting. My understanding is splat and broadcast are the same thing, but I'm not sure. But yeah, essentially this is doing pretty much something similar. So you have an element-wise op on a bunch of broadcasted values. You can just do the element-wise op first and then broadcast it. Something like if you're doing like, I don't know, add of 1, 2, 3, 4, you can just do the add first and then expand it to like whatever. So if you were doing like a tensor of 1024 dimension, adding 1 to it, or like adding sort of a adding like multiply of 1 into 2, you can combine it in such a way where you actually do the element, the 1 into 2 first and then broadcast the value, which is 2. Then there's so yeah, I think there's somebody mentioned like essentially data flow. I mean, this is more like actually like data load and store, so sort of slightly different, but yeah, they do some uh, operations on actually the pointers to convert them into some standard form. This is fairly complicated stuff, so I didn't really look into like what this does. But loop unrolling is another. I think this is fairly common compiler optimization technique as well. So yeah, so there's a bunch of these like Triton specific passes, and they're defined as part of this table gen file. Now, if you go a layer below, then there's Triton GPU specific passes. So if we go into that, you will see some familiar things. So there's GPU pipelining. You have, there's apparently this trick called 3 into TF32 trick, where you can decompose like a floating point 32 dot op into 4. So yeah, Triton uses a bunch of these cool things under the hood to actually like optimize your code. So there's DPU prefetch, accelerate matmul. So I think then it essentially checks. Yeah, I think this is for tensor cores from when I was looking at the code. Optimize dot operands. So yeah, there's coalescing. So all of these are sort of defined here, and then you will essentially have the actual implementations and in the code gen. So we'll cover one of these in the later slides. So I know, Mark, you asked the question. So there's actually specific NVIDIA specific passes too. So my understanding is a lot of the stuff was originally just in the Triton GPU passes, and they sort of split them up into NVIDIA specific and sort of common ones. And I think this work is sort of still ongoing. And I'm assuming as more custom hardwares are targeted, like a lot of the common stuff, it sort of more starts splitting into like more dialects, essentially. So yeah, this is just summarizes that it does a bunch of optimizations like coalescing, 432 dot product optimization, CTA planning, etc., etc. So yeah, I mean, if folks are interested in like what all it does, the table gen file is really easily readable. So you can go through like, oh, like this is a cool trick that it's doing or something like that. So yeah, I found it really, really readable and like interesting. Now we can maybe, I know we sort of, so yeah, we can quickly run through like an IR. So this is the GPU IR, because you can see it has like sort of more NVIDIA specific stuff now, or actually not NVIDIA specific, but it's, I actually don't know if like AMD has a concept of warps or not. But yeah, I mean, I only have NVIDIA device, so I'll just focus on CUDA. But yeah, if you look at here, this should look pretty familiar. So we have like the TT program ID, it gets the PID. Actually, let's go to the next slide. Yeah, so first of all, like the module that's defined has a bunch of attributes. So essentially, it's figure like this is just the metadata for the kernel essentially. So you have how many threads per warp, what's the target GPU, number of warps, etc. So this is defined at the top in the module. So now if you go to the next stage, you get this is essentially your block size. Then you have your PID. You take your constant 1024. multiply it with the PID. So yeah, it's once you start looking at it, you can map it back to the Python code, Python DSL code. Now there's a bunch of like broadcasting and add operations. So as I mentioned, there are existing dialects that that Triton relies on. So those can actually also be found in the table gen file. It will actually show you dependent dialects. So like arith just provide like arithmetic operations. So here it's essentially adding the %2, which is this range with the constant, or like I think it's the it's the broadcasted value that's coming from the constant, I think. But yeah, there's a bunch of like, so this is the actual operation where we're adding the A and B together. So this is just an add float here. So it's doing a float 32 addition. And whenever you have any sort of input pointer and output pointer, you should see a bunch of load and store ops, which does do some optimizations on. I think it does coalescing, so it will move memory around and stuff like that. So yeah, super interesting stuff. I took all of that and essentially put it into like a graph-based like a digraph thing, and I just put in like what each Python line of code is doing as part of the IR. So essentially you take, so this is where everything starts. You take the PID. This is the block generation, and then you have the offsets. Then you load your X and Y, you add them together, and then you store them in the final output here. Now, if we want to look at, let's say, go one layer deeper into like what gets out of the table gen file, we can look at like an example. Now, whenever you have a custom pass, you will probably see like three references to it. One is like the actual table gen file. The others would be the actual implementation, and then everything is sort of available through PyBind modules because the compiler stuff is all on in Python. So if we go to the actual implementation here, now a bunch of this is like MLIR specific stuff. So this is fairly generic. But if we go line by line, this is just getting a context. It's getting what op it is, and then it actually checks like what is the NVIDIA compute capability. So I'm assuming it's looking at like what generation of NVIDIA device it is, etc. And this is, I mean, just standard MLIR stuff. No idea what it does, but it is an MLIR namespace. So now, I think this is where most of the work is happening. So if you go into here, you see it's figuring out warps. It has like versions of like how many warps per tile it will generate, etc. And then it will check whether it actually doesn't even support anything compute capability below 70. And you can get shapes per CTA, get number of warps, CTA layout. Yeah, I mean, it's doing a lot of stuff, but yeah, if you want to read through it, I think like feel free to like poke around with this. Now, and I annotated the actual generated the matml pass with like the actual documentation. But yeah, the MLI documentation is actually pretty good. So yeah, a lot of useful info there. Okay, I guess let's. So I came prepared because I was not sure whether live coding will go successfully because my other computer fan just started blowing up for some reason and machine just dies. So I prepared beforehand. So what I did was, so let me. So I already have this Triton repo checked out. So yeah, so And so I essentially just added a couple of extra passes to the common Triton passes. So let's go here. So if we wanna, let's check. So yeah, this is the passes. So this is your actual Python package where you have this is the common passes function that I had originally mentioned. So you can see like all of the specific modules where the actual so the Python side compiler will just call into these methods over here, and these are just all wrapped through or wrapped through like PyBind. So I added, I mean, I didn't want to deal with any new arguments, so I just took like two void taking compiler passes. One is it will just generate like op graph. So essentially, after your TTIR is done, it will actually just print your op graph. And the other one I did was just I took like op stat. It will give you like how many or just an op counter, essentially how many ops you have for a specific op. So super simple stuff. So if I show you diff against the main, it essentially just takes. I added this new pass, and within the actual compiler, I added like a new print ops graph, and in the LLVM pass, I added this like ops stats pass. So let me just show you in the code, so it might be easier to see. So here's the ops pass. So this is part of when it makes the during the make LLIR call. And if we look at op graph, this is just after like you go through all of the actual TTIR passes here. So let's run this again. Let's clean our cache, and I'm gonna MLIR enable dump. Whoops. Okay, I am in the wrong directory. Lectures, lecture 29. Okay. Okay, so it dumped a bunch of stuff. I'm just gonna quit out of here and then let's go. So if you see here, it now started putting the op stats after the LLIR is generated, or I think it's doing it just before. It's interesting. Maybe there's some ordering issue because it technically should have done it after this one here, but that's fine. And if you go all the way up to the TTIR generation, it should have, there you go. So it dumps this like digraph thing, which oops. So it just prints an op graph of like what is going on. Once I just copied it over to see, like it just generates something too big, so it's really not useful to see for somebody like me. But yeah, this was just I wanted to just poke around with like if I could add an extra pass to the compiler. Yeah, so now I added like a bunch of sources that I used to learn about this stuff, but mostly like I actually read a lot of code within the Triton repo. That was super helpful. I use the debugger a lot to just understand like how things are flowing under the hood, and the and yeah, I think like I use the MLIR documentation to learn about like what MLIR is. I actually got interested in it from one of Chris Latner's podcast with Lex Friedman. So yeah, it was yeah. I mean, it was a fun project, like side project, to learn about ML compilers. That's all I had. So yeah, okay, thanks.
This was sick. Kapil, thank you so much. Folks, please shower Kapil with emojis. Thank you so much. Okay, so I think now we can move on to Q&A. I'm going to open up the chat and zoom in on Kapil. All right, so let's see. All right, folks. Yeah, Kapil the man, thanks for the MLIR video. You're getting hearts and flame emojis. Let me see if there's a question in here somewhere. All right, some questions about GraphViz. Okay, I think no new questions. Okay.
I think there was like one question like, how is Triton different from MLIR? So what's the main difference, maybe to summarize?
Oh, what's the difference between Triton and MLIR? Yeah, I mean, Triton, so if you were to think of, the analogy would be Triton is like C, C++, and MLIR is like GCC or Clang. I think Clang is probably a better example. Because Clang provides a bunch of like tooling around, like compiling your C, C++ code. So Clang is like an ecosystem. So essentially, you have Clang Tidy, which can use Clang to do a bunch of linters and stuff. So yeah, I think like that's probably a good example. Like if you were to think of Triton is sort of like C, C++ code, and Clang would be your MLIR. Yeah.
Samiran is asking, can you build graphs inside of Triton?
Can you build graphs inside of Triton?
Data flow graphs.
What's data flow graphs? I would think you could, but you'll probably have to write a custom pass for it. So you could probably just, I would think you should be able to, but I think it probably would take a custom pass to do that.
I also see another question, like how does Triton go from PTX to SAS? Yeah, I think the answer there is just NVIDIA proprietary libraries. And yeah, indeed, Dani Khan is confirming this as well. Okay, yeah. All right.
So one question regarding the graphs that you generated. This was quite interesting. You said you used GraphViz for it. Was like is there some existing transformation which you used in order to generate this?
I used an LLM to generate this.
Oh, really?
So yeah, I mean, spoiler alert, LLMs are really good at generating diagrams. So you can just, if you want to like print out any sort of flowchart and you want to use GraphViz for it, just ask an LLM to do it for you, and it will just write out the whole diagraph plan and just copy paste into an online GraphViz visualizer, and then you get everything. Yeah.
Okay, perfect. Right. So Samiran is also mentioning there's a flag which will generate GraphViz from MLIR or LLVM. Yeah, if anyone can find this graph, that sounds great. Okay, Phil's saying he doesn't trust LLMs for diagrams. Okay, and then it's like, all right. Well, yeah. I mean, I guess I did really appreciate like the extensive references and tooling you had. So I felt like your talk is also best appreciated if people like go back and like rerun their own experiments. So I assume you have no issues sharing your slides with people, and we'll add them in the lectures repo.
Yeah, I mean, I essentially have everything in the checked out lectures thing. I'll send a PR for it. Yeah.
Sweet, thank you. That makes our life much easier. Thank you. All right. Well, Kapil is on the server, and he was like our first returning guest, I think, as we mentioned at the beginning. And so, if you have any other like Triton questions to ask him, like he's here. And Kapil, honestly, thank you so much for coming on. We just like this was a fantastic talk.
Thank you very much. Super interesting and also challenging topic.
So for next week, we have another person who's from our server, and we discovered from the server called GoNurst. And he's basically very quickly become like one of the core contributors of the Torch.io project. And he's going to be talking about quantized training. So basically how to do training in an 8x8. And he also has some very early experiments of like getting bit networking in pure PyTorch using the compiler with some custom Triton kernels. Yeah, like QAT. GoNurst is absolutely brilliant. So yeah, I hope to see everyone next week. And thank you everyone. And again, thanks again, Kapil.